Hi, everybody. In the next 30 minutes, I have the pleasure to present you some of my learnings from many years of experience in demand forecasting in specific and time series predictions in general. So after a very brief introduction into our use case of demand forecasting, the talk will be split in 10 different concepts. And don't get worried if you get lost in one of them. They are only loosely coupled, so you can just jump right back into the next one. Demand forecasting is very important for supply chain management, with the most prominent example being its usage as a forward-looking component in order optimization on the different stages of the supply chain. So demand itself is a random variable and it comes time-tagged. So that means this thing is about time series forecasting. You can see such a time series in the plot on the left side. So, and the different stages of the supply chain also come with different flavors of demand. So on the lower end, on the retail side, demand usually comes as point of sale. So that means sales is your target, looking at sales data in the past. So this can be from grocery supermarkets, fashion shops, also online shops. The typical prediction dimension there is product, location, date. So the item in this store on a given day, for example. And you have many influencing factors available like prices, promotions, and so on. And you usually see a quite regular demand pattern coming from the fact that when looking at the full day, you're basically not looking at an individual customer, but something like an average customer behavior. On the other hand, if you look higher up in the supply chain and more on the manufacturing side, you see demand usually as orders. So that means a retailer, for example, ordering at a consumer packaged goods company. So there, the customer, if it's a big retailer, can be important as a potential additional prediction dimension. So this is one of the aspects that leads to this famous bullwhip effect that the uncertainty gets higher, the higher you go up in the supply chain, what is depicted actually in the right picture on this slide. So also you have usually fewer available influencing factors here, so which makes this a bit tougher to predict in the end. So one thing to mention is that the target here can also be censored data. So for example, in the case of retail sales data, there can be out of stock situations or markdown sales that you actually have to correct for when you want to do a proper training. So the first thing to mention here is why we would actually use machine learning instead of a traditional univariate time series forecasting method. So that you want statistical learning from a business perspective is clear because your automation is crucial here. So if you look, for example, at a typical retail grocery chain, you have thousands of items, hundreds of stores that you want to predict daily, and you definitely don't want to do this manually. So, but why use machine learning and not just the univariate time series methods? So the first reason is that you can do a combined learning on all of these time series. So in the univariate time series forecasting, you would do an optimization individually. And in machine learning, you can just combine all of them. And by exploiting the commonalities between different attributes or hierarchies in the data, you could drastically reduce the variance. The other thing is that with machine learning, you have natural consideration of external variables. So this can be prices, promotions, weather. So such things you could just use as features in machine learning. And by doing so, you would drastically reduce the bias. So in the plot on the lower right side here, you see the time series of one product summed over several locations. And you see a weekly pattern, basically. And overlaid, you see quite an increase in sales in the blue period, which is actually promotion. So there's a promotion active, and this would have the effect on the sales that it goes up dramatically. And this you could use simply as feature in a machine learning model, for example. So that means what you will see in the following is that I will use this famous bias variance trade-off of statistical learning as example in some of those concepts. So here actually it would mean that you get a reduction both in variance and in bias if you use machine learning over traditional methods. So you should definitely use it. So nowadays, all of the buzz in machine learning is actually about deep learning. But what I want to show you is that you should not just write jump onto deep learning and ignore feature engineering completely. So feature engineering can outperform feature learning dramatically, actually. And the reason for this is that you can include domain or prior knowledge by doing so. And this beats pure learning from data usually. So because this is kind of a combination of the bottom-up approach of machine learning from pure data and top-down models, including this prior knowledge. So and this can, for example, come quite handy if you want to learn specific, potentially rare effects. So the plot, the upper plot shows a time series where you have, again, a quite prominent promotions effect. So this is something that you can basically just include as a pure flag, but there can be other things that are very important. For example, the duration of a promotion. So a promotion might be damped towards the end, for example, and giving this a specific feature can be quite helpful for the model. Another example would be if you think of weather. That is hot in the summer, so the pure temperature as raw data is not very useful for a method, because this is something that happens all the time. But the first sunny weekend, for example, can create such a sales spike, for example, and this you would like to have a specific feature in your method. Otherwise, it is quite difficult for the machine learning algorithm to find it out by itself. Another example that goes a bit further is you can also include a sub-estimator in your model, for example, the price-demand elasticity. So in the lower plot, you could see on the x-axis the relative price, which is basically the reduced price divided by the normal price of a product, and the demand on the y-axis. You see that the lower the price, the higher the demand, and this comes with an exponential form in this case, and is also modeled as exponential. And the slope of this elasticity, you could actually categorize in different parameters. So you could have a parameter for each store, for example. So this would reflect the fact that maybe in different regions, the people show a different price sensitivity in terms of their demand. So as having something like this as feature in the model is quite helpful. And if you go even a bit further, you could also think of product attributes that you would or hierarchies that you would learn from images of a fashion web shop, for example, or from the description of products. So that means in the end, I would say you definitely should not feel ashamed of feature engineering. It can help to improve your models a lot, especially in demand forecasting. Okay, an often underestimated topic in machine learning methods is the preprocessing of the features. So a lot can be gained if you use statistical methods in a clever way here. So I will show you two examples. So the first one is the binning or discretization of continuous features. So what is a good method there is something that I call here equistatistics binning. So this basically means that you arrange it in a way that you have approximately the same number of observations in each bin. So by doing so, you can actually remove outliers, which might help to stabilize your method a lot. Going a bit further, you can use on top of binning a smoothing approach. So this would first of all look at each bin and consider in each bin the target mean. So this means a target encoding. So in the upper plot, you would see the different equistatistics bins for this feature, and you see the data points as the target means in each of these bins. And then you could actually fit a spline or orthogonal polynomial or any other functional form through this data. And going forward, you would then not use the raw data points, but use the fitted data points. So by doing so, you would ignore all these fluctuations that you see in the plot, which drastically reduce the variance and could get rid of lots of overfitting. So and this actually comes completely for free. Another way, you could also think of this as another way to include prior knowledge. So in the lower plot, this is the time trend. So you see data over several years or with a seasonality. and also with a trend that's going up over the years. And here the functional form that you are fitting is just a straight line. So you basically have just a linear time trend, which you could use also to include this knowledge. I will come to that later on again. So definitely you should make use of preprocessing. And one more example of the bias variance trade-off is the encoding of categorical features. So if you think of demand forecasting, the index of the samples we are looking at besides time is products and locations. And products and locations usually come as IDs. So that means here you have two very important categorical features that you want to use to basically learn the effect from individual time series, even if you do the optimization of all of them together. And two possibilities to use them as machine learning features would be first, you just do a separate treatment of each category. So this is basically what you see in the upper plot. So there we have here one category for each item number, and you would see here again the target mean in everything in every bin. Doing so basically means that you need the capability of a method to deal with high cardinality of such categorical features. Another possibility would be that after the target encoding, you would actually put everything to a single variable. So that means you use the target means in each bin and just put them in one single variable, which you see in the lower plot. So this can also be, instead of the mean, to include the trend, for example, you could also use an exponential weighted moving average for this. So of course, always looking only in the past of this product location combination. The two of them are preferable in different situations. So basically what you see is that the separate treatment has a higher variance but a lower bias. So, and vice versa for the mean encoding, and it depends on the situation in which you are in. So usually you would say if you have not much external information available, it is safe to jump on the mean encoding method because it reduces the variance, and there is not so much to learn from the other features. And in retail, it is often preferable to actually use a separate treatment because you can make use of the correlations with all other external features. So in the end, it is very important that you think about it and treat your categorical features well. They are very important. Okay, so now we go a bit beyond the pure machine learning and look into possible applications for demand shaping rather than forecasting. So that means I mentioned before that statistical learning and machine learning is just curve fitting in many dimensions. If you really want to tell something about the causal structure in your data, you need for an add-on to machine learning. So machine learning and data are not enough to describe the causal structure. And such an add-on is usually a causal assumption. So what we want in the end is we want a method that allows us to predict something that is called counterfactuals, which is the fundamental problem of causal inference, which asks what could have happened instead. So what is the issue is that you have usually only one realization. And you cannot observe different potential outcomes. And what you want is to have the individual causal effect between such different outcomes. So one example for this would be demand shaping via price setting. So this is such an exact causal what-if scenario when you say the price was $2, but what would have happened to the demand if the price would have been $3? And of course, you want this forward-looking. So that means you somehow need the method that enables you to do so. And machine learning is one ingredient to this because it provides you with the individualization via its generalization capabilities. And the other ingredient is deconfounding. So for this, let's first look what I mean with confounding. So in the diagram, in the upper diagram here, you could see three random variables. So X would be, for example, the price that you can actually set. So you have the possibility to change this feature. And Y would be your target, which is the demand which you want to influence. So that means you want to to know the causal effect from X on Y. But the issue now is that there are other variables depicted as Z here, which would have an influence both on X and Y. So let's say, for example, the day of the week would have an effect on the demand because more people go shopping on weekends. But it might also have an effect on the historical data that you have from price setting because you just reduce the price more often on the weekend, for example. So, and you want to get rid of the influence from Z on X here to actually make a statement about the causal effect from X on Y. So, and there are different methods that you could use. So the easiest one is, of course, randomized control trials. So that means if you can set the price randomly, you would get rid of this dependency of Z on X. But often you are left with observational data and you have actually no chance to do so. So then what is another possibility is that you use independence weights by means of propensity scores that are potentially learned from another machine learning model. So by doing so rid of the dependency in your observational data. But you could also use some partial deconfounding. So this is sometimes good enough. And smoothing that I mentioned before can be used to partially impose causal assumptions. So an example is the lower plot here, which shows you day of the year as feature. So you see the seasonality. And what the smoothing function is here is basically a sine. So you would not allow for wiggles in such a smoothing function, and you see lots of fluctuations of the data, also spikes maybe coming from promotions or so, but you would not allow them to be learned by this feature, by just having a smoothing function of a sine here. So this would be a causal assumption that this feature could not affect more. And this is often enough to actually have a bit of causal assumptions in your method to just pimp it to do something like demand shaping. Okay, besides the implications on causal decision making, a special kind of confounding can also affect the effectiveness of your demand time series forecasting itself. And I call this temporal confounding here. In the upper diagram, you could see what I mean. So Y again is the demand, and you look at the demand at time t. So let's say today, and at time t minus 1, let's say yesterday. So what you usually have with autocorrelations is that you have a statistical dependency between yesterday and today. But this is actually, at least the bulk of it, is not a causal effect. So this is actually a spurious correlation coming from the fact that you have a confounding with all the other causal effects on demand. So for example, if there was a promotion yesterday, there is a good chance that there is also a promotion today. Or if yesterday was summer, there is still summer today. So that means you have a common cause for the two times here, which leads to a correlation between the two. And this autocorrelation is actually what is used by most state-of-the-art time series forecasting methods. So including recurrent neural networks, for example. So they basically use select target information to do most of the learning. Of course, they also might also include all the external features, but the learning of their effects, especially of peaking structures, is much harder if you have the lag target information overlaid. So that means if you want to improve things like explainability of your model, mid and long-term forecasting quality, which is not relying too much on autocorrelation, or the predictability of rare spiking events, it is usually better to strive for direct learning of the causal effects. And an easy way to do so is you just not using lag target information in your machine learning model. So you just drop it from your model. So, but then of course you might lose information because here you have all kind of hidden information in that you might not have in your other features. So to include it again, you can just use a subsequent residual correction on the finest granularity. So that means on product location granularity. So this you can do to capture all kind of missing trends. So for example, via an exponential moving average over the deviation between the predictions and the actual sales. You could see an example in the lower plot here. So this is about the beginning of the COVID crisis this year. In yellow, you could see the sales, which is suddenly rising for this product group at some point. And you see that the machine learning method in blue, which is not including leg target information, would not predict this. But the dashed line, which is after the residual correction, would just react to it in kind of an online learning after the first days, where it would see a deviation between the two. So in the end, my advice is separate the autocorrelation. This can help a lot to learn specific effects. So now we come to an interesting little effect that cannot easily be treated with a single machine learning model. And this is the direct influence of one sample on another. So the famous use case in demand forecasting here is cannibalization and halo effects. So what does this mean? So cannibalization means that the demand of a product decreases due to another product, for example, in promotion at the same time. You could see this behavior in the plot. So here in the upper plot, you see a product that has a huge sales increase when it comes to promotion, which is visualized by the red periods. And there might be another product, the lower plot, that has a quite stable sales behavior, but is actually dropping when this other product goes to promotions because it's losing sales to this other product. It's get cannibalized by it. So this you could actually do with an additional machine learning model after your main model. So you have a main model that gets you the predictions, including all other effects. And then you look at the residuals as targets. And what you do is you learn individual parameter for each product pair in kind of a product matrix form. And you only use pairs where one is in promotion. So you need kind of a trigger event. This does not have to be promotion. It can also be another trigger, like, for example, an out-of-stock situation. And in the end, you also want to have some feature selection to avoid overfitting in such a product matrix form. And this can be a quite good method to capture such effects. So actually employ residuals in such cases. Okay, so an ever more important aspect of machine learning predictions is trust, especially when it comes to business critical use cases. So what you want to have in the end is an individual explainability. This is visualized in the plot here. So what you could see is a time series where you see the ingredients of a prediction. So the different factors shown here show you the different features of such a model. So for example, the price, events, weather, and so on. And you see their behavior over time. So that means you see what make up the prediction of an individual product location combination at each point in time. So this shows, for example, that at the first 4 days in this plot, there was maybe a reduced price, which drove the demand high, and then it's dropping, for example. And you could also see the weekly structure overlaid in the calendar factor here, for example. So such an individual explainability helps, of course, a lot to dig into root causes for example, too high predictions or something like that. So one famous method to get there is generalized additive models. So what is also useful is if you use a multiplicative model here. So you could see it in the formula what I mean by that. So this is again with the former method of binning. And such a multiplicative model can come quite handy because then you directly get the different features as factors like in the plot. Usually a multiplicative approach is also better than an additive approach for many features because it helps you to learn the right level of uncertainty. So basically, if the variation is proportional to the level, it's better to have a multiplicative model. So in the end, what is important to note is that you should not confuse such an explainability with the causal structure. So this would actually have, you would have to employ some causal assumptions. This here would only give you the inner workings of the model. So definitely you should try to build trust with white box ML, however you do it. Okay, so far we have only spoken about point estimations, but in fact, what you really want are predictions of full probability density functions. So because these are crucial for subsequent probabilistic decision making. So for example, by minimizing a cost function. So let's say you have different risks. So in a retail setting for order optimization, this might be stock out risks or overstock risks. So by having a full probability density function, like in the plot here, you could choose a low quantile of the PDF for ordering and would have low overstock risks, but high out of stock risks, and vice versa for high quantiles. So, by knowing your costs, you could actually use this to optimize your cost function optimally. So there are different ways to get to such a PDF. So one would be a parametric approach, where your demand is modeled according to some PDF assumption. So this usually a negative binomial is a good choice for retail cases. So this would account for over dispersion compared to a Poisson distribution, for example. And you would best use different machine learning models for both mean and variance. And having then mean and variance and the causal assumption, you would have the full PDF. An alternative would be an empiric density estimation. So for example, via a quantile regression. So this is of course more flexible, but it's also less robust than a PDF estimation. So then if you have such a method, you of course also want to check the goodness of your PDF prediction in the end. So that means you want to evaluate them. And here I just give a few suggestions how you would do it. So on the left side, you see a PDF, which you could convert then in a cumulated distribution function. And then you can actually look at the actuals compared to your prediction, which is the dashed vertical line. So you get CDF observations, so to say. And by having such single CDF observations, you could not tell much about the goodness of your PDF estimation. But by looking at many of them together, so for example, by filling them to an histogram, you could come to a conclusion. So such a histogram you would expect to be flat. So that means a uniform distribution. And any deviation from it would actually hint to some flaws in your method. So this you could also do in a quantitative evaluation by means of looking at deviations from the uniform distribution in terms of, for example, the earth mover distance or Kullback-Leibler divergence or something like that. And you can go even one step further in the direction of qualitative evaluation by not looking at the histogram itself, by actually looking at profile plots according to some other variables. So in the case on the right plot here, you have the mean prediction on the x-axis, and you have different quantiles on the y-axis where you just compare your CDF observations in a lower, higher perspective. And by doing so, you could see first deviations, for example, in low quantiles or in high quantiles, but you could also see deviations in specific areas of the variable you are looking at the x-axis. So, and this can be very helpful to really pinpoint to some flaws in your method. Okay, and that's it for today. So, of course, there are many more aspects to this extensive topic, but I hope that you had some fun with the 10 selected, and thanks a lot for your attention.